supposed to be working. So, did you guys go over the suggested problems? Because I can answer any questions you might have about those now.
I went through the 4 problems from the book pretty okay, but I got stuck on the one you posted on Canvas. Like I tried a lot and I tried different approaches and I just...
Okay, yeah, I can go over that one for sure. So let's share my screen. Oh, I have to. Cool. Okay. Screen. Okay. And then, okay, so I'm gonna use, yes, this should work. Cool. Okay, so the problem, which I can't see right now, I'll have to pull it up right here. Okay, so the problem was to find the solutions for this system. And we have 4x2 minus 2x3 8x4 equals 12. And then, okay, so I'm going to just copy this down. So of course, the first step is going to be writing this in, like putting this into an augmented matrix so that we can use our row operations on it. Right. Okay, so this is our system. Wait, let me go back. Wait. Okay, this is our system, and I'm going to write it as a matrix. So I write the coefficients and then a vertical line, and then on the other side I write the those constants. So since we're missing those variables, we write zeros there. We have -1, 7, and then 1, -7, -2. Oh, sorry, shifted over. So 0, 1, -7, -2, -4, and 0, 0, 1, 3, -5. Okay, so hopefully you got this far, right? And the first thing we want to do is swap these two rows. And the reason we're doing that is because this leftmost entry is, well, we want to put it as high as possible. So actually today we're going to go through an algorithm for doing this. So we'll actually have like steps that you can follow, and they'll always work for row reducing a matrix. But just by looking at it, we can see that if we want that step-like behavior, we need the third row to be in the second row. So the row operation we're going to do is just to swap those two. And then we will get everything else stays the same. And then we write 0, 1, -7, -2, -4, 0, 0, 5, -1, 7, and then 0, 0, 1, 3, -5. Great. Okay, so what we want to do next is we have a leading entry right here, and we want zeros underneath it. So there's only one row that's below it. We want a 0 here. Let me just do this in a different color. We want this to be 0, okay? And we can do that using our replacement row operation, where we'll take that fourth row and we'll use the previous row to eliminate that 1, okay? So what we would need to to do. So we can take the third row, and in order for that 1 to go away, we'll need to multiply the third row by 1/5 and then subtract it from the first one. Right? Okay. So just writing out all of those steps. So minus 1/5 row 3 is going to look like -1. We'll get positive 1/5. Oh, sorry, I started from the middle of the row. So we would have 2 zeros. Then we'd get -1, 1/5, and that'd be -7/5, right? And then we want to add that to the fourth row like that. So just adding these together. I'm going to move it down a little bit so I have room to write my matrix. So put it here. Let's see, and also move this over, honestly. Okay. Let's see. So let's compute this first. So we'll get 0, 0, 0. That's good because we wanted to get a 0 in this particular entry. And then we have to add 3 and 1/5. So that would be 16/5. And then this one, it would be, we would have -25 minus 7. So that would be -32 over 5. Right. And then we'll copy down the other rows from our previous matrix. So 1, 4, 1, 4, -2, 8, 12, 0.
Hi, didn't me.
Sorry?
Just checking. So you could also multiply the last row by -5 and then add.
Yes, you could do that. And then you would avoid the fractions.
Okay.
Yeah.
Thank you. I don't like the
How to-
fractions.
yeah, that's fine. Totally fine. So there are more than one, there are multiple ways to do this, but it will be equivalent, right? What you end up with. So here you go. This is in row echelon form, right? Yeah, I know. So this is your step-like behavior, right? And at this point, you can then use back substitution to get to your answer, right? And if you really don't like those fractions in the denominator, you could multiply 3 by 5 to get rid of those. Yeah. Yeah, so that would be your answer. I mean, this is not your answer. You still need to go find the solution, but at this point, it shouldn't be too difficult. So I'll skip that if no one wants to see it. If you want to see it, I can do it.
I'm a little confused as to like just what it means to find the solution.
Yeah, okay. Well,
Like literally what find the solution means, like what the final answer should look like. Sorry.
yeah, no, that's totally fine. So we'll go over that. We'll actually be talking about that more today as well. So you'll see more examples during class. Okay, so what I'm going to do first is take care of this like nasty fraction. And I can do that by multiplying row 4 by 5. And then I'm also going to divide by 16 since 16 divides both 16 and 32, right? So what I'll get in the last row is just 1 here and then -2, I believe. Right. I think that's right. And so just filling in the rest of the matrix, 0, 5, -1, 7, right? Okay, So now we have it in this form. Okay. And I can, like I said, we can use back substitution. So I'm just going to write out what the system of equations will be using these coefficients. Equals 12. We then get x2 minus 7x3 minus 2x4 equals -4. We get 5x3 minus x4 equals 7, and then x4 equals -2. Right, so we have one variable that we know, and then we can use that to work backwards. So starting with the next equation up, I will just plug in -2 for x4. So it would look like this. We would get 5x3 equals 5. So x3 equals 1. Right? Okay, so that's two of the variables solved for. Then we use the next equation up. We get x2 minus 7 times 1 minus 2 times -2 equals -4. And so x2 will be 7. That will give you +4, so -4, minus another 4, so -1. And then, so we get x2 equals -1. And then lastly, we just use the last equation. Right? So we're just systematically finding each of the variables from our system of equations.
And we're using we're starting at the lowest, the bottom row, and we're basically just using whatever we find on that bottom row. And then we just keep on going up using our solutions to fill in the blanks.
Yeah.
Essentially.
And this works when you have this perfect like step behavior. So you have a leading entry in each column, right? And it goes all the way down. That's how you like bootstrap your way back to.
So it's really important in order to solve systems of equations like this that our bottommost row only has x of n populated plus the augmented value, right?
Right. Yeah. And if you had all zeros and then just something in the like augmented column in the last column, that would make your system inconsistent, right? So at that
Yeah.
point, you can just
Okay.
conclude it's inconsistent. If you have this behavior, we can use back substitution. And then the other possibility, remember, is that we have infinitely many solutions, and that's what we're going to talk about today, later on, how to write down the solution set in that case, right? Okay, so just to finish this up, we plug in the other values. We'll have -2 plus 8. What is x for? -2 equals 12. So we get this is what? -22. So x1 equals 34, I believe. Let me know if I make like a arithmetic error because I'm very prone to those. Okay, so we have our 4 values, and that means that our solution we can write down. We always write it down as an ordered, I guess we would call it a 4 tuple in this case because there's 4 entries, but we just write it as an ordered list like this. So 34 minus 1, 1, and -2. And this is the solution. Okay. I haven't been checking the chat. Okay. Okay, so that's that problem. Does anybody have any questions at this point?
Oh, yeah, I have just a question about the row echelon form. Like once you get in that form, do you have to take a step further and make it into a reduced row echelon form, or can you just jump right in?
You can do it further. Right. So you could keep going with your row operations if you know, like them, you don't mind doing that. You can do it, put it in reduced row echelon form. And then once you have it exactly in reduced row echelon form, you can essentially just read your solutions off. Well, in this case, if you have, you know, infinitely many solutions, it's a little bit more complicated. But if you have a unique solution, then you'll just have your answer like right in front of you. Yeah. Yeah. So I have to pull up my notes real quick. And stick them here. Okay, cool. Now, so I was going to do a little, oh yeah, sorry, I need to. I don't have them on. Should work. It's always issues. Okay. I can. Huh. Okay, I got it. Cool. This is right. Yeah. Okay. So I was going to do a little bit of review of what we did last time. So just talk about the elementary row operations. So what we did last time was essentially define linear equations, define systems of equations, talk about solutions, that they can be consistent, inconsistent, or consistent or inconsistent, and they can be unique or not unique. And then we talked about matrices, specifically matrices of coefficients and augmented matrices. So those are the two that we're working with right now. Mostly we use augmented matrices because they help us solve systems of linear equations, right? We had the following elementary row operations, right? So does anybody remember, let's see, just one of those?
Replacement.
Scaling.
Replacement, interchange, and scaling.
Yeah, exactly. So I'm starting with interchanging. That one's kind of self-explanatory. Also scaling, pretty self-explanatory. You just multiply a row by a non-zero constant. Okay, and then replacement is a little bit hard to state, but we can describe it. So just you can just this means that you replace a row with the sum of itself and a constant multiple of another row. Okay.
I have a question.
Yeah.
Can you do the other way around? Sum a constant multiple of itself and another row? Or does the scaling have to be on the other row that's being summed?
No, you could scale honestly both at the same time.
Okay.
Yeah. But you could also split it into two steps and scale first and then do the replacement. So the more things you do at once, the more likely you are to make a mistake. So just be careful when you're doing this. Yeah. Okay, so those are our three elementary row operations. And then we went over row echelon form. So I'm going to go over that again. One thing I will say about when we're performing these row operations, what you get when you do a row operation like say, I'm not going to write out the matrix, but say we had a matrix and we wanted to interchange two rows, and we would write it like this, right? The reason we use an arrow is because these two matrices as matrices are not equal, right? So you really should use an arrow, not an equal sign, when you're doing these row operations, because you are changing the matrix each time, right? You can also, so the textbook, I think, uses a squiggle like this between row operations, and that's pretty common as well. Just make sure you're not using an equal sign. Right? Use arrow or squiggle, not an equal sign. Just write this out. Between row operations. Okay. So we had row echelon form. So I'm going to start abbreviating this REF just because we'll be writing it a lot, and it's nice to have an abbreviation. Let me see. Is it okay to write row? This will act as the new row 2. So I would write it in order of, so I would put row 2 goes to 3 times row 2, right? So you start with what you have and then what you want to end up with, like, or what the new thing is going to be, right?
This hurts my head. For me, the way I process it is what you're doing is multiplying row 2 times 3, and that becomes the new R2. I process it differently.
Okay, yeah. Yeah, I'd like it for you to, I mean, maybe if you wrote the new thing first and then the old thing and then the arrow. Is that
It doesn't gel with how my brain works, but I'll write it that way because that's
okay.
the convention.
Yeah, for sure. Okay. Here is row echelon form. So the first thing is that all, I'll put it this way, all rows of all zeros are at the bottom of the matrix. So if you have any rows of all zeros, they occur at the bottom, right? And then we can easily get to this using our row operations by just interchanging, right? So we can just push everything to the bottom that is all zeros. And then each leading entry of a row, and remember, a leading entry is the first non-zero entry when you're moving left to right across a row. So each leading entry of a row is in a column to the right of the leading entry of the row above it. Right. So just to give a quick example, so in this matrix here, right, we have the first leading entry occurs here. In the second row, the leading entry is here. And in the third row, the leading entry is here. And each time the leading entry is to the right of the one above it, right? So if you're comparing these two, the first row and the second row, in the second row, the leading entry is to the right of the leading entry in the first row. The same goes for comparing the second, excuse me, and the third row, right? So this is a non-example. Let's see. here, if we have 0, 1, 0, 0, 1, 0, 1. Okay. So in this case, the leading entry of the first row is in the second column, but the leading entry of the second row is in the first column. So it's not going in the right direction, right? Is it okay if all the numbers after the leading number is 0? Yeah, that's totally. It's really, so there's a picture in the book I'll probably pull up after I finish writing down the row echelon form and then a reduced row echelon form. Actually, after, I'll just write down the last thing for row echelon form and then I'll pull up the book if I can. Okay. Did you have a question?
Yeah, so I suppose this is more of like a conceptual question that I had.
Mhm.
So I'm really used to like two-dimensional planes and working like conceptualizing with vectors.
Mhm.
And I noticed that on the book, on page 6, it showed the series of equations that we were working on as planes, and that was like a really alien conceptual concept, I guess, like higher dimensional use of like planes, I guess.
Mhm.
And I plugged it into my graphing calculator, and it was really cool to watch, like all the system of equations turn into planes all with a single intersection.
Yeah.
And my initial thought is, um, I want to innately work with them as vectors. Would it be like wrong to think of them as vectors? Would it be more correct to think of them as planes?
It depends on what is it that you're thinking of as a vector? Like
A line.
so like you're looking at a row and seeing it as a vector, or
So I I guess like since the examples that they gave for when I think of like a system of equations, I think of like high school algebra 2, finding the intersection between two lines on a Euclidean graph.
Yeah.
And um, so like my mind wants to think of intersections as like where two lines intersect. And in three-dimensional space, you have another axis, but you can still have a line in three-dimensional space. So my question is like, should I think of them as planes, or should I think of them as just a line in three-dimensional space with an intersection?
So it wouldn't be like if you had a system of equations in 3 variables and it's like sitting in R3. So you're thinking of it as in R3, your
Mhm.
equations are not necessarily going to give you lines. I think they won't ever
Yeah.
give you lines. They're always going to be planes, right?
Okay.
So they're generally one dimension less than the ambient space or the space that you're sitting in.
Yeah.
So in the case of R3, you're going to end up with planes. In the case of R2, you end up with lines. If you go higher,
Um,
you end up with higher dimension.
would it be accurate to say that there's a hidden, so when you're working with two-dimensional equations in R2 space, would you say that it would be conceptually accurate to say that there's a hidden uh, like one times x3 property that we just can't see? So it is actually making a plane, but we're only viewing it on the xy axis, so like we can't see that, because that would make a lot of sense to me. So like every single dimensional is actually there.
Mhm.
Um, yeah.
You could think of it that way. Like you could imagine just like extending it in another direction and you would get like an equivalent sort of
Yeah.
system. Yeah.
That's like such a cool concept in my mind, to like take all of like my middle school and high school like plotting, and to just like add like another dimension that was there all the time, and like the lines are actually extending in that direction, and we just can't see it because it's plotted two-dimensionally.
Right. Yeah. How to imagine higher dimensions. Visualize. This is a higher dimension. Okay. Yeah. I mean, thinking about higher dimensions is fun, of course. So yeah, I have my own thoughts about it, but maybe we should get to the new material. Okay, so just to finish up row echelon form, we have this not correspondence, but this relationship between the leading entries, and then also all entries in a column below a leading entry are zeros, right? Okay, so let's see. Oh yeah, I was going to see if I can, I probably have to try to share from this one. Okay. Where's the textbook? Here we go. Okay. So hopefully you guys have access to the textbook, and you may have already seen this if you looked over this section before today, but I'm going to show you this page right here. So you see these matrices. These are showing you what a row echelon form will look like without actually filling in the values. So here, these boxes, the squares just mean any number that's not zero. The stars could be zero, or they could be any other number, right? And so the idea here is just to show what this would look like. And notice that these zeros occur on the bottom, like left of the matrix, right? Generally. Okay, so okay. I'm gonna go back to my screen and let's see. Here we go. Okay. So that is the row echelon form. And then we had the reduced row echelon form, which the first condition, sorry, I did use okay, I'll write this out this time, and then I'm going to start using the abbreviation RREF for reduced row echelon form, okay? And so the first condition is that the matrix is in row echelon form, so standard row echelon form, and also that the leading entries are all 1. And let's see, the last thing is that the leading entry in a, or oh, how do I put this? Leading entry is the only non-zero entry in a column. Okay. Okay. Cool. So any matrix can be reduced to row echelon form. But row echelon form is not unique, right? We can have many different forms of that for a particular matrix. But you can also further reduce to reduced row echelon form, and reduced row echelon form is unique. So for any given matrix, the reduced row echelon form, there's only one way that you can write that. It's all you will get from one matrix at a time, right? Does that make sense? Okay. Uh, okay, so I'm going to write down a few matrices and I want you to just determine which ones are in row echelon form and which ones are in reduced row echelon form, and try to be able to explain in words why it is that it is, you know, one of those or neither, right? Okay, so two. Spaces. Okay. Okay. So there's 4 of those. Yep. Okay, so does anybody have an answer for, let's say, the first one here? I'll give them numbers so we can refer to them. Yes, the first one is in neither row echelon form or reduced row echelon form. And it is because there is a 1 in the leading entries column. So the leading entry of the first row does not have zeros below it, right? So this is the problem right here. Okay, so right, this is neither. Number 2 is in row echelon form and reduced row echelon form, right? So if a matrix is in reduced row echelon form, it's got to be in regular row echelon form, right? Right. So we can see that we have each of the leading entries is 1, and they have zeros above them, or how do I say this? They're the only non-zero entry in their column. So if we focus on the first one, we have that 1 and we have all other entries are 0. And then if we focus on the second column, all of the other entries except for the 1 are 0. And then in the third, or sorry, in the fourth, the same thing. Notice in the third column, we don't have a leading entry that occurs in that column. So there's not really a condition on what that column needs to be, other than that it can't interfere with this step like the echelon form, right? So if it had entries here or here, it would interfere with that. Otherwise, it can be whatever it wants to be. Right? Maybe I'll just undo. Okay. Let's see. The third is in reduced row echelon form, but is inconsistent. Very true. Yes, it is in reduced row echelon form, and it's inconsistent because of that last row. Right, we get 0 equals 3. Can it be in reduced row echelon form? Yes, if it is inconsistent. And that's actually how we tell if it's inconsistent, is usually to put it in row echelon form or reduced row echelon form. And then we can see from that whether the system is consistent or inconsistent. And it's if we end up with something like this, where we have zeros as our coefficients, and then in the last column, we have something that's non-zero. That forces it to be inconsistent. Okay. And then the fourth is in row echelon form because the second leading entry is non-1. Yeah, exactly. This is the second leading entry. It is not equal to 1. It is also inconsistent because we also have, right, that 0 equals 5, which is not true. Right? So this one is in row echelon form, but not reduced row echelon form. And it is also inconsistent. Oops. Oh, geez. Okay. Okay, great. So good. So,
For reduced row echelon form, you have to have a non-zero in as the leading entry, but if 0 is the leading entry, then it's just reduced, or then it's just row echelon.
sorry, I didn't hear the last part.
If 0 is a leading entry, then it's reduced echelon form, but if it's a non-zero, then it's reduced row echelon.
So we can't have 0 be a leading entry. It's the first non-zero entry in a row, right? So what I'm confused by what you're asking.
I'm trying to compare the row echelon form with reduced row echelon form, and
Okay.
where I can visualize that.
Right. So for instance, if we compare this one, which is in reduced row echelon form, to the one below it, which is in just regular row echelon form, one thing that was pointed out is that one of the leading entries is not a 1. That means that it's not in reduced row echelon form. Also, if we focus on this, I'll use a different color, this column right here, right? We have a leading entry. Suppose it was 1 and we were still trying to figure out whether it was in reduced row echelon form or not. There is a 1 above it, which is non-zero. And that is another condition that it doesn't satisfy, right? Because if you have a leading entry, everything else in that column should be 0, right? Okay. That makes sense? Okay, cool. All right. And so I think last time I went over the definition of a pivot. So I'll give it to you again because we're going to kind of expand on it. So a pivot is the leading entry of a row in a matrix that is in row echelon form. Okay, so the leading entry of a row in a matrix in row echelon form. Okay. So, for instance, if I just use the example number 2, I'm going to rewrite it so it's less messy. But so we have these entries. 0, 1, 0, 0, 9, 2, 0, 0. Okay, so we have this particular matrix. The pivots are going to be just each of the leading entries. So these ones, right? And then we'll have something else, which will be called a pivot position. Which is going to be the location or particular entry that corresponds to a pivot in the original matrix. So usually we talk about pivot positions when we start with a matrix, we row reduce it, get it into that row echelon form, and then we figure out where our pivots are because we can tell once it's in that form where they are. And then we look at the original matrix and we circle the places where the pivots occur, right? Those are called the pivot positions, right? Okay. Okay, does every matrix have a row echelon, reduced row echelon form equivalent? Or is it impossible for some? It's possible for every, yeah. And there's exactly one, exactly right. Okay, so pivot position and then a pivot column is going to be a column containing a pivot position. So just to give an example before we move on, but without going through all of the computations, this example we will do in a second, but I will tell you now that what it row reduces to, right? So we have 6 minus 5 minus 9, 4, 8, 6. Okay, so this particular matrix will row reduce to 0, oh, okay, 2, 0, 2, 1, 1, and 5 minus. Okay, so the pivots, let's see. Okay, I think someone asked this last class, but I forgot the answer. Can we pop that bottom row off the stack? No, we should not do that. Right? A homogeneous column slash row. So what do you mean by homogeneous?
I remember when working with like dot multiplication, we're supposed to keep like a column of ones so that we don't accidentally reduce the dimensionality of our data set.
I see. I don't know that they act in the same way, but you should just carry them along. Right? Okay, so here we have our row reduced matrix. So it is in row echelon form, not reduced row echelon form. But from that, we can tell where our pivots are, right? They occur here, here, and here. And then the pivot positions are just the ones corresponding to those highlighted entries in the original matrix. So it's just this one, and this one. And again, the pivot columns are going to be these ones that contain a pivot, right? So these are pivot columns.
I have a question.
Mhm.
So if like in the process of row reducing the matrix, you flip rows, the pivot points are still in the same, like you don't flip them with the row.
No, you don't flip them with the row.
Okay.
They just, yeah, exact correspondence. Okay, so what do you call the pivots? Since the numbers change. Right, so when we refer to a pivot, it doesn't really, how do I say this? It doesn't really matter what the value is, so long as it's non-zero, right? So remember that when we're in row echelon form, it's not unique. So we might have a 1 here, like in this particular spot, or it could be a 2, and it would still be a pivot, right? So it's really about the position and it being non-zero. And it's not so much about what number it actually is. Does that make sense? Okay, cool. So our pivot columns are the first, second, and fifth columns.
Sorry, I do have a question.
Mhm.
You said as long as it's non-zero, but okay, never mind. So the things that you highlighted in the upper matrix, those aren't pivots. You're just showing us where the pivots will eventually go.
They are pivot positions, so that's different than pivots, right? Okay, so here, a pivot is the leading entry of a row of a matrix in row echelon form, right? The position is sort of like tracking backwards to the original matrix and just marking it there. Does that make sense?
Okay,
Okay.
but it says it corresponds to a pivot in the original matrix, but the original matrix doesn't have pivots, only pivot positions.
Yeah, because this is the original.
Okay.
Okay.
Sorry, I'm confused. It's okay.
Okay, yeah. It's probably easier to just think about the reduced, the row echelon form of the matrix and visualize it there, right? That's what we usually work with in any case when we're talking about pivots and when we're talking about pivot columns.
Professor, I think Veronica might be confused because you said that a pivot is a leading entry of a row in a matrix in a reduced echelon form. But then in the definition of the pivot position, you mentioned a pivot in the original matrix. Based on your definition of a pivot, there can't be a pivot in the original matrix.
Thank you.
Okay.
Yeah.
Let's see.
Thank you, Bo.
Location or particular entry. So I'm saying, oh, it's in the wrong spot. Okay. Particular, how do I say?
Would it be accurate to say that a pivot position is a discrete object from a pivot? They just happen to be where pivots are located on the REF, but they're almost separate entities.
You're considering them separately, but there is a correspondence, right? There's a relation.
Yeah.
So the position is the location in the original matrix. And I'll just get rid of this.
Oh, I see what you meant now. Okay. Okay.
I'm sorry about the wording. I think it was probably pretty confusing. Yeah, in the original matrix, it corresponds to a pivot in the row echelon form. Oh, oops, that didn't work. Okay, cool. So we will talk about the pivot columns again in a bit, but we're going to go over that row reduction algorithm that I've been referring to. So this is a row reduction algorithm. Algorithm just means a sequence of steps that is always going to give you what you want, right? So this is just
Is this the steps to like solving a system of equation using the matrix?
right. So it is getting you nearly there. So it's just
Okay.
for,
It's something that we've been practicing. Okay.
yeah, so we've been doing this without this algorithm. So this is just giving us some steps that you can always use, right? Okay. So this is for putting a matrix into reduced row echelon form. That's what you can use it for. It will also get you to row echelon form. And if you stop before the last step, then you stay in row echelon form. The last step is to get you all the way to reduced row echelon form. Okay, so the first thing, so I'm going to write a step and then do the step using this matrix right here. Okay, so we'll be using that as our example, and we'll be working through it using the algorithm. So if you have a leftmost entry, so if a leftmost entry does not occur in the first row, so if it occurs somewhere in another row, not in the first row, you can swap it with another row. Okay, so just to copy down this matrix again, 12, 4, 8, 6, and 5, 9, and 15. Okay. So looking at this matrix, you can see that the leftmost entry would be here or here. You could use either one, right? So both of those are farthest to the left. In the first row, we have a 0 in that position, in that column. So we want to swap it with another row in order to get a leading entry that occurs in the first row, right? So what we can do, I'm going to go ahead and swap the first row with the last row, so row 3. You could also swap it with row 2, but works out nice if you swap it with row 3. So we just do this step. And then put the first row on the bottom, -5. There we go. If you get, okay, so it's possible to have a system where, say, the entire first column is zeros. So you wouldn't have any constraints on x1, right? That wouldn't, so your system doesn't deal with x1 at all. It doesn't tell you any information about it, but it's still there as a variable. So it wouldn't be insolvable. It would force your system to have infinitely many solutions, right? Yeah, and we'll talk about that hopefully today. So let's hurry up. Okay, so here we have the first step, and then the second step is going to be that you use the first row to clear the column below. So what we mean by that is that we can use replacement, right, to eliminate any of the non-zero values in the column below your leading entry that you're focusing on, right? So this is the leading entry you're focusing on, and you want to clear this 3 right here that's sitting beneath it, right? Okay, so what we can do is replace row 2 with row 2 minus row 1. And then we'll get those 3's to cancel, right? So the first row stays the same, so we'll just copy it down. And the second row will have row 2 minus row 1, so we'll get 0. -7 minus -9, so that will give you 2. 8 minus 12 would be -4. -5 plus 9 would give you 4. And 8 minus 6 is 2, and 9 minus 5 is -6. That should be right. Okay, and then the last row stays the same. Okay, so that means we have all zeros beneath our leading entry in the first column, so we move on to the next step, right? Okay, so step number 3. Oh. I skipped step 3 in my notes. That's funny. Okay, but there is a step 3. So you move to the next row. In fact, I'm going to put this on the next page. Oh, I can't. Oh, well. Okay, so step 3, you sort of ignore the first row now. You just move on to the next one. And you look for your leftmost entry. So if the leftmost entry does not occur in that row, you have to swap it with the lower one where it does occur. Okay. So in our example, that's not necessary because our leftmost entry, use it, oh, different color. Our leftmost entry right here does occur in the next row, right? So this is not necessary in our example. So we move on to the next step, step 4, which is going to be to use the row from step 3, the one with the leftmost leading entry, and you use it to clear the column. So similar to step 2. Use the row from step 3 to clear the column in which the leading entry occurs.
I have a question.
Mhm.
Are we clearing just the rows below the second row, or do we clear all the rows?
You clear, oh yeah. I didn't put that in there. So you clear down.
So you clear the column, you clear the part of the column that's below the leading entry. Cool, thank you.
Okay, to clear the column. Okay.
Sorry, if you were going to do reduced row echelon form, would you also clear the row above it?
Yes, and so
Okay.
you want to clear the column above the leading entry as well, but you don't want to do that yet, right?
Okay.
Yeah, so you go clearing below, so you clear down. I don't know how to put this in like proper words. So clear the column moving down. And then when you get to the end, then you start clearing up. Right?
Because you don't know where the entry points would be, right?
So
Well, you do, but
it's, I don't know how to put that in words. So the reasoning behind that, I guess you can think of it as you're sort of establishing your pivot points, right? When you put it in
yeah.
a echelon form, then you use those to clear what you need to, right?
So you can clear more than one column per row, right? Like if you could turn, even if you're in reduced echelon form, you can continue to turn out, or you can continue to clear columns and push everything further and further, right?
I'm not sure that I follow.
So like the bottom row there,
Mhm.
after you get rid of the 3, you
Mhm.
could potentially also just continue like down and get rid of the -6 and the 6 until you're just left with the 4 and -5 or whatever that would be at that time.
It's not necessarily the case that you can clear those values. It depends
Okay.
on whether you have a pivot or a leading entry in that row, right?
Yeah.
That's why we do this systematically and we sort of move from left to right. Okay, so here we are. We need to clear this 3 that we have right here because it's below our leading entry. So what we can do first to make this a little bit easier is scale by 1/2 our second row. So multiply through by 1/2 for that second row. And you will get 0, 1, -2, 2, 1, -3. Right? And then we'll clear the row. So using replacement, what we want to do is replace row 3 with row 3 minus 3 times row 2. Okay. Okay, and then we would get a 0 here, and then let's see, we multiply this by -3, so we would also get a 0 there. -3 times 2 would also cancel out the 6 there, and then we would get 1, 9, and 4. Okay. That is where we are after step 4, and we are in row echelon form, right? We can see that we have our leading entries moving left to right, and that's what we need for row echelon form. And then, wait, let's see. We can put this in reduced row echelon form. So the first thing you have to do is scale so that you have leading ones to have, let's say, ones in the leading entries. Or I say ones as leading entries, right? So you would want to scale by, oh, oops, I got the wrong thing here. Okay, this is your pivot. So there's really only one that you need to scale. It's the first row, right? So scale the first row by 1/3, and you will get 1, -3, 4, -3, 2, 5, and 0, 1, -2, 2, 1, -3, 0, 0, 0, 0, 1, and 4. Okay. And then the last step is to clear upwards. So before we were talking about clearing down. So you want to clear upwards. What we mean by this is to use, so starting with the rightmost pivot, you want to use replacement to clear the column above that pivot. So you should have zeros below it because it's in row echelon form, but you want to get rid of the stuff above it. So for instance, here we have a pivot in the 5th column, and we have stuff above it that we want to get rid of. Great. Okay, there was a comment. You had to scale multiple rows. Could you do it all at the same time? Yeah, that's something that I think is safe to do. You could scale all of your rows at the same time because there's not that interaction between them. But if you're trying to do like 2 replacements at the same time, that would just be really bad, most likely. So, yeah.
Is it dangerous to write multiple steps at once? Like, is that why you suggest doing the one step and then rewriting the whole matrix?
Yeah. So until you get comfortable with doing it, I would say write one step at a time. Once you do, you could do more than one, but like I said, don't do more than one replacement. It's like most likely you should not do that. That's just my suggestion. Okay, so what we can do is then clear. So finishing off this, I'll just do one step actually. So we'll clear this particular one, and then I'll leave you to finish off the rest. So the way that you want to do this is you take row 2, replace it with row 2 minus row 3, right? That will get rid of your 1, and then so we have the last row. Next row, since we have all these zeros, it doesn't affect the first 4 entries of this row, right? And then in that column, we get a 0, and then we get 4 minus 3, so 7. And then 1 minus 3, 4, 5, like this. And then you would do a similar thing to get rid of the 2. And then you would also, so the things you have left to do are get rid of this 2 and get rid of this minus 3. But I'm going to skip that because we are almost out of time and I really want to get to solutions. Okay. Okay, so let's talk about solution sets. So we've seen examples where we have a unique solution. And when we have a unique solution, then we just write the solution down and put it in little set brackets. So for example, I was going to have you guys work on this problem. So maybe I'll just assign it as a suggested problem for you to do before next time to get some practice. Of course, you also have the homework, so you'll get practice doing that as well. So it would be, you can reduce this down and you should get a unique solution of 1 minus 2, 3. So as a solution. So the solution set is going to be just, so we use these like curly braces to denote a set, and then we just have one element inside the set, and it is that unique solution. Right? Okay, but what if your system has infinitely many solutions, right? We said that that was one of the options as well. Okay, so for example, if we had if we had a system and say a system that row reduces to something like this: 0, 0, 0, 1, 0, 1, minus 1, 0, and minus 4, minus 1, 0, like that. Okay. Then notice that we have all zeros in the last row, so that means that this does not tell us that it's inconsistent. In fact, it is consistent, right? Because we have all zeros. What we can do is we can write down the solution, right? And so let's just note that what we get when we write this as a system of equations, we get x1 plus x2 equals minus 4, and x2 minus x3, oh, sorry, this is supposed to be x3. x1 plus x3 equals minus 4, x2 minus x3 equals negative 1, right? That's our system. So what we're going to do is define basic variables and free variables. Okay, so our remembering that these columns correspond to one variable each, right? We'll say that x1 and x2 here are basic variables because a pivot occurs in their column, the column corresponding to those variables, right? So if we label them, we see there's a pivot here, there's a pivot in the x2 column, and there is not a pivot in x3. So x3 is a free variable because no pivot occurs in the x3 column. Right. Doesn't look like a 3. There we go. Okay. So just to be really clear what we mean by a free variable. So just, we can see from this example, but just to be very clear, a variable xi is a free variable if its corresponding column is not a pivot column. And remember that we defined pivot column earlier today. That was just a column in which a pivot occurs, right? Okay, so using this particular example, so this is a free variable. How we write down the solution set is we let x3 equal t. So we take that free variable and we replace it with a letter that's going to correspond to or represent any real number. Okay. So then what we get, remember we had x1 plus x3 equals -4 and x2 minus x3 equals -1. We're going to rewrite these both by pulling that x3 to the other side. So we get minus x3 minus 4 and x2 equals x3 minus 1. And then we're going to replace x3 with t, right? This doesn't really change anything, right? But it's going to help us just keep in mind that we're sort of letting x3 be any number, and each value of that is going to give us a new solution. So that's our infinitely many solutions. Okay. So we would get this t minus 1. Okay. So we have an expression for x1 and x2, and remember that x3 was t. So we can write down what we will call the general solution. So this is what we will do when we have infinitely many solutions. We'll write this as minus t minus 4 for x1, right? So we're writing it as a solution as we normally do, but instead of having numbers, we have these things that depend on t and t, right? Okay. So that is going to be how we write down the solution in this case.
Could we replace it with t with x3 instead?
Yeah, it's not like strictly necessary for you to use the t. It's just, it makes it look a little nicer, right?
Okay.
So if you've worked with like parametric equations before, we usually use like t or something like that. So it's just to emphasize that t is like a parameter that we change, and for each t we get a new solution.
Okay.
So instead of it being like corresponding to a particular variable, we're sort of like writing it in a new way. Does that make sense? Almost, maybe.
Yeah.
Would it be accurate to say that we're almost like tying it to x3?
Yeah, so the solution is tied to the value of x3, and depending on what x3 is, you get a new solution. So that's why we call it a free variable, because it's allowed to vary. And then the other solutions or the other variables depend on that value. Right? Okay. So this is the general solution. You can give your answer like this generally. That's what you would do if you're looking for the solution for a system. You have infinitely many solutions. Your answer should be the general solution, and it should look like that. You can also write down the solution set, and that would just be your general solution. So you would write these curly braces again, and then write, I guess, I don't know what you use, the vertical line. So this means points of this form such that t is a real number. Okay, I don't know how familiar you guys are with like set notation. You may or may not be. It is. That's terrible. Okay, we did make it 2 solutions, so that's good. For next time, I'd like you to look over 1.3. So I will also put that information up on Canvas, and I'll put these notes up on Canvas and the recording. So I'll see you guys next time.